Yeah, 16,000 times faster. And this isn't about going from bad code to good code. We are starting with a decent implementation. Moreover, everything we do will be non-asymptotic optimizations. So we will keep the same big O complexity while still getting faster and faster. So let's go and start with the puzzle. Here you can see the classic chess programming puzzle, the 8 queens problem. And today we are going to write a solution for it and optimize it as much as we can. So the goal is to place 8 queens on a chessboard so that no 2 queens threaten each other. Here you can see some of valid solutions. And for example, this one is not a solution because there are 2 queens on the fourth row. And also queen on h4 is threatening the queen on d8 on the diagonal here. This one is also not a solution because of 2 queens on the G column. Okay, so the plan. We will be solving generalization of the problem called n queens. And our task will be to find the total number of placements of n queens on an n-xn chessboard. We will start with somewhat good implementation in Python, at least in terms of big O. Then we will try to optimize it, still keeping everything in Python and compare the result. In the second part, we will switch to Rust and get some simple optimizations here. And in the end, we will squeeze every last bit of performance out of Rust implementation. Okay, so first implementation that come to my mind is a backtracking algorithm. The idea is to have an array of size n, their index represents a row on the chessboard, and the value at that index is a column where the queen is placed, and for unoccupied rows we will have an -1. When we start our recursive backtracking from the first row, the base case is when we reach the last row, put in every queen. And recursively, we will check every column, but only if a square is not attacked by any other queen. And to check if the square is not attacked for every previous row, if the column is occupied, or if the main diagonal is occupied, or if the anti-diagonal is occupied, we return false. Otherwise, it's safe to place the queen there. Okay, so time complexity of this solution is big O of n factorial, because on each step of recursion, we will have to check every possible placement, which is reducing by 1 on each step. So it will be n times n-1 times n-2, etc. until 1. And for every step, we will also call is square safe function, which is big O of n itself. But for theoretical big O analysis, it's getting absorbed by the factorial. Obviously, it will be our first optimization target. Okay, and to check the performance of this implementation, I will run hyperfine with the few different values of n and take the minimum of 50 run. I will test n from 8 to 16 for the first implementation. Later you will see why. But for some time after, let's focus on n equal 12, because everything above that runs too slow for now. So here is a chart of performance of our first implementation. First n's until 12 are running fine. We are in terms of milliseconds. Then on n equals 12, we hit in 3 seconds. And then each time it's getting much slower and slower and slower and slower until we hit unacceptable 117 minutes on n equals 16. Since I don't want to wait 2 hours for each test now, let's focus on n equals 12. Okay, so we have noticed our is square safe function is not very efficient, so let's try to optimize it first. One thing we can do here is to replace our column list with a couple of sets representing occupied columns and diagonals like this. Now we can check if our square is safe in constant time using set lookup. So this code collapses this. For sure, now we need to keep our sets updated, so we need to update our solve function from this to this. Here, we are still iterating over every possible placement column, but now we are keeping our sets updated. So it looks like we are doing more work here, but is it really worth it? Especially considering the theoretical time complexity of the algorithm is still the same. Well, let's check it. And yes, new solution is running much faster, and I have got 730 milliseconds on my machine. Okay, so changing our state type helped with performance. Probably we can find something even more efficient here. Maybe let's try list here. They for sure introduced back the end factor we just got rid of, but they are also much more efficient than sets on small sizes. So in the main function, let's replace our sets with lists. And in the solve function, replace adds with appends and removes with pops. A square function will be the same as before. So what about the performance? It's not that bad, but we have lost a bit here. Inversion is running about 780 milliseconds, which is 50 milliseconds slower than our favorite. Considering that it will only get worse with bigger n's, let's ditch this idea for now. Okay, so probably we can use another approach here. What is more efficient than sets for numbers from 0 to some relatively small n? Bitsets. So the main idea is that we can represent our sets as an integer, where each bit represents a number in the set. For example, here could be our number 3, or this could be 8. So if the value is not in the set, the bit will be 0, and if we add 8 to our empty bit set, it will become 1. Bitsets are actually very efficient in terms of memory and performance, since we can use fast CPU-native bitwise operation to manipulate them. Exempligrate, in the following bit set, to set our 8 bits, we can use bitwise OR like this. Then, to reset it, we can use bitwise AND. And to check if the bit is set, we can use bitwise AND again. Okay, but before we celebrate, let's check the performance of the Bitset version. I will not show you code changes just yet, but they are very similar to when we replace sets with lists, except for some non-local declarations. Okay, so new version is 1.1 seconds. It's even worse than with lists. Yeah, since it could be tempting to use some low-level tricks in Python, it's not always the best idea. And the golden rule is, don't make conclusions about performance, measure. Okay, so crazy idea. What if we use a bitset again, but instead of storing our bits in an integer, we store them in a list like this. Now, to set a bit, we use indexing. And we use indexing to add set it to, and to check if bit is set, we can use indexing again. It's a pretty simple operation, and as we said, small lists are in general more efficient than sets, and now we get rid of n as a factor we had in our previous list implementation. Moreover, it doesn't require much operation to get to the bit we want, like it was with the bitset. So, and for performance of this implementation, I got 395 milliseconds, which is almost 2 times faster than our previous favorite. Nice. Maybe we could try optimize it even more. I actually did experiment a bit with some Python-related micro-optimizations, but none of them showed any significant performance gain, and I have ended up with just 5% faster than our favorite. So let's not waste time on this and just jump straight to another programming language with amazing performance, Rust. Blazingly fast. But before we do that, I would like to mention one good solution for Python when we are facing CPU-bound tasks like this, and for some reason we can't optimize our code any further. JIT compilers. One of the most popular JIT compilers for Python is PyPy, which is actually an alternative Python interpreter. Another one is Numba, which can be used as a decorator for your functions, and it will compile subset of Python code to machine code. Both have their own limitations, but they are worth checking out. So for the PyPy version, all I did is run the same code with another interpreter, and it's running almost twice as faster for free, 210 milliseconds. And for the Numba version, I had to rewrite the code a bit, get rid of the nested function, and after applying Numba decorator, it was much slower, 1.4 seconds. Not that great. I could probably try to make it better, but instead, let's get rusty. So for the Rust version, let's straight up port our most performance Python solution with lists. And since I didn't actually show you the Python version, you can finally see the changes. So we start with declaration of our bit lists for columns and diagonals. Then let's define our solve function. This time, as we don't want to have a closure here, we have to pass all needed context as arguments to our state as mutable references. And we will call our function as in Python version, starting with row 0. And inside the solve function, we again have the base case, then loop over columns. And inside the loop, first we have to calculate our list indexes for the diagonals. When we can check if the square is attacked by checking all our lists here. And finally, we can recursively call our solve function for the next row. Of course, we also need to update our list before and after the call. Oh yeah, and we need to store and return the result of our function, of course. So this is our first Rust implementation. Let's check how it performs. Before we had our favorite Python version running for 395 milliseconds with CPython. And the same version with PyPy was running for 210 milliseconds. How about Rust solution? Well, it's 225. Nah, don't worry, it's a debug build. And in release, I have got 38 milliseconds. It's about 62 times faster than our first implementation. But we are not done here yet. Let's check what else we can do with the code. Do you remember we had slower bitset version in Python? Will it be faster in Rust since its numbers are closer to the metal? Let's try it. So in the previous solve function, let's replace our list with bitsets. Let's not pass them as mutable references since values itself very small and could be passed by value on the stack. Then, as we start with empty values, we can just pass 0 to the first function call. And inside the solve function, we can now use bitwise operations to set our bits. So this version transforms to this. Notice that now we don't have to restore our previous values since we are passing our bitsets by value. So if previous algorithm was correct backtracking, this one would be depth first search, even though changes are minimal. Okay, so let's check if the changes were worth it. Our previous example was running for 38 milliseconds, and this one is 39, about 20% faster. But it's kinda hard to see here, so I want to do a little switch in the chart. Instead of showing the time in milliseconds, let's show the speedup factor compared to the first implementation. So our final Python implementation was running about 4.6 times faster, then PyPy version was about 14.3 times faster, then first Rust implementation was 62.4 times faster, and finally our bitset version is 76.8 times faster. Yeah, so now it's easier to see the relative difference and we can continue with optimizations. Okay, for our next optimization, let's check how we iterate over our columns. In our current version, we are checking every column. Then, for every column, we check if it's occupied or not. And comparison is pretty expensive, especially considering that with logical OR, there are actually 3 separate branches, and it's hard job for CPU branch predictor. We can do much better here. You can combine the comparisons into a single operation like this. The difference is that now all 3 expressions will be calculated always, but now it will be only a single branch instead of 3. And branch itself, it's relatively easier for the branch predictor. So what's the performance? It's a simple change, but it got us pretty good performance boost. It's running for just 22 milliseconds now, which is about 1.7 times faster than the free branched version and 136 times faster than version A. But believe me or not, we are going to ditch this version because there is even better way. Currently we have 1 branch, but how about 0 branches? Here, before even iterating over columns, we can calculate the bitset, representing all columns that cannot be attacked by any queen we already placed, by merging our sets and applying mask representing the whole board. So the whole board is a 2 in an nth power minus 1, which is a bitset with n bits set to 1. And our merged bitsets are just a bitwise OR of our column and diagonal bitsets. And to get the available columns, we take all the columns and remove ones that are attacked. Simple. Let me merge it into a single expression to save some screen space. And now, instead of iterating through all the columns, we can pick a bit from the bitset one by one until the bitset is empty like this. And to actually pick a bit, we have a bit magic, this one. Okay, we almost done here, but probably you have already noticed that we cannot just merge our bit sets, since in different sets bit index represent different things. For our column bit set, it's okay, every bit represents a column index, but for diagonals there is a problem. Since index is a diagonal one, not related to the column index, but it have an easy elegant solution. We will just shift our diagonal bit sets in the directional of the diagonal to move the bit to the right place. So where we pass our bit sets to next recursive call here, just shift them to make indexes match. Okay, so what was the last change we need to get rid of the for loop and our branch? Let's check how it performs. I have got just 6.4 milliseconds for this implementation, which is 3.4 times faster than the single branch version and 468 times faster than version A. So we're getting closer to the number I have promised you in the title. And for next optimization, I would like to focus on a chessboard again. So in our algorithm, we start with our first row, putting n queen in the first column. Then, with recursive call, we scan all over rows, but it's not important exactly how we do it. Just notice that we are getting some number from it. So after that, we move the queen to the next column and get a number again. Then third, then fourth, and finally, interesting thing happens when we reach the fifth column. We actually don't need to calculate the number for it because we already know it, thanks to the symmetry of the chessboard. The actual number of placement will be the same as for previous column, and symmetry will be preserved until the last one. So basically it means that we can calculate the answer for the half of the position and then multiply it by 2 with extra care for the middle column if n is odd. Let's try to implement it in the code. This time our solve subfunction will remain the same, but we will call it differently now. Instead of simple single call starting with row 0 like this, we will iterate through half of it by ourselves here. After, we for sure need to double our result and to handle middle column like this. And that's it. We paired with increased complexity for the bootstrapping code, but theoretically we should get a speed up by a factor of 2. Let's check if it's true. And almost. New version is running for 3.6 milliseconds, which is about 80% faster than fastest version so far, and about 832 times faster than version A. But 3.6 milliseconds, it's pretty small number, and there is some overhead from starting the benchmark itself, running binary, etc. So to make comparison even more accurate, let's now switch to n equals 60. Since almost all previous versions were too slow for this n, we will compare A and version starting from H now. So rerunning the benchmark for them on n equals 16, there A is running for 117 minutes, H is running for just 9.4 seconds, which is about 737 times faster. It's almost impossible to see the A value here. And I version is running for 4.8 seconds, which is almost 2 times faster than H and 1463 times faster than A. Okay, so what's next? Probably you're already waiting for this one for a while. My CPU, as probably yours, has multiple cores, but they are only using one of them. If we take a look at our main loop here, we can notice that every call is independent and can easily be run in parallel. So as an easy solution, let's just use run create. First, let's convert this loop into an iterator like this. Then we can just add into per iter colon it, and Ren will take care of the rest. Let's check the performance. So while effectiveness or our solution stayed the same, we can utilize more resources now. And our new version is running for 0.7 seconds. It's 6.9 times faster than a single-threaded version and 10,000 times faster than version A. But while 7 times speed up sounds like a lot, my CPU actually has 20 cores, so I am not satisfied with this. Actually, since we are only iterating over half of the columns, our maximum speed up is n divided by 2. Which is 8 for n equals 16, and even less for smaller n's. So we need to do better. Obvious and simple enough solution will be to split up into threads on second level, so we will have n more subtasks to give to our CPU cores. To do so, we will need embed 2 recursive calls instead of 1 in our main function, collect the tasks, idest call parameters we will put into threads, and iterate through it instead. So let's implement it. Again, our solve function remains the same, but instead of iterating through columns, we will need a collection of tasks like this. We will put everything we need to calculate in this vector. So first change is that we can just return total sum as a result now. And second change is, since we need to also pass multiplier here, for our symmetrical task, it will be 2. And for central column, it will be 1. Okay, so let's fill our vector now. First, we will iterate through every column like before, when we collect arguments for our first level, our 3 bitsets. When we start our second level, build our avail bitset first and iterate through it. And inside the loop, we can finally collect a single task. But don't forget about the middle column. After this loop, we need to iterate to repeat the level 2 loop again here, building our avail bitset. Then, again, same loop over it, except this time multiplier will be 1. Here is an overview of the final version. Now let's check how it performs. Our previous version was running for 0.7 seconds, and new one is 435 milliseconds. It's about 1.6 times faster than version with poor utilization and more than 16,000 times faster than version 8. Okay, and I would actually like to finish right here. Before that, let me tell you what I have tried and what didn't work. I have tried playing with Python micro-optimization. None of them showed any significant performance gain. Digging into generated bytecode and assembly, I didn't find much there, at least for my level of understanding. I tried to manage the threads manually instead of using Rayon. It didn't help either. I tried architecture-specific optimizations, but LLVM applied them already. And also I tried to rewrite the final solution to C++ and Zik. Both gave me about 10% speed up, which is a lot. It shows that there is still room for some optimizations. Some more thoughts. There is actually a O1 solution via precomputed values. It doesn't satisfy me for 2 reasons. First, this value need to be calculated anyway, so we need an algorithm to begin with, and waiting 5 years for initial numbers is not an option. Second, is just not fun and wouldn't allow me to show you all these optimizations. Okay, and takeaways from this video. Measure instead of guessing. Common sense or experience isn't always right. Tools you use could make a big difference, sometimes for free. Optimization is a process requiring creativity and trial and error approach. Don't give up on an idea if it doesn't work at first. Something that works in one language doesn't always work in another. And last one, even keeping the same big O complexity, we can get a 10 or 100 or 1,000 times performance gain. Okay, and that's all for today. I will be really happy to hear your thoughts on this video, and I'm planning to do more on both topics, performance optimizations and chess programming. So subscribe to get more videos like this, and I will see you in the next one.